Hello students, myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of optical communication, I am going to deliver before you error control techniques in the receiver section of the optical communication and the eye diagram, which is one of the most important parameters in the deciding the performance of a receiver. Already we have discussed about the receiver sections parameters which decided performance in the previous lecture also. In this particular lecture, I am going to cover before you different error control techniques and the eye diagram. Before going through the error control techniques, first of all we have to know about the different types of errors which are occurring in the optical communication. So, here are some of the errors which are occurring in the optical communication. Here are, so the what are the first of all what are the reasons for different types of errors which occurs in the optical communication. So, the different types of reasons for different type of error as the noise, crosstalk, etc., which basically corrupt the incoming signal during this transmission process only, and data link layer uses some error control mechanism. Then when the error get occur, the data link layer uses some error control mechanism to ensure the frames, that is what is the frame, basically it a data bit streams are transmitted with certain level of accuracy. But to understand how error is controlled, it is essential to know what type of errors may occur. So, these are the some common types of errors. The first one is the single bit error, second one is the multiple bit error, and the third one is the burst error. So, first of all, the first type of error, single bit error. Single bit error in a frame, you can easily say that this, if the bit are in a particular stream, then it is called as a frame. That is why in a frame is mentioned here, because bit are in a particular stream. In a frame, there is only one bit which is corrupted, then it is called as single bit error. For example, 10110011. So, you can say this is the signal data which has been sent, but received is what? 101101. You can see here it is 1, but what we have sent? We have sent 0. So, a single bit is corrected in a stream, then it is called as the single bit error. Now, multiple bit error. So, in the case of a multiple bit error, the frame received with more than one bit is corrupted, then it is called as the multiple bit error. So, what are in the sender end? 10110011, and what is received? 101, this is the error, 0, this is the error. Here 0 and here 1 is transmitted. So, we can have a more than one bit which is corrupted. So, that is why it is called as the multiple bit error. So, one thing we can have, in burst error also multiple bits get corrupted, but what is the difference? In burst error also you can see that more than one bit are corrupted. You can see this 3 is corrupted, but in burst error, all the corrupted bits are in the consecutive form, are in continuous condition, but in the case of a multiple bit error, it may be, it will be one by in a different position. It is not in a continuous format, consecutive form. That is why it is called a multiple bit error, and this is called a burst error. This is one of the difference between the multiple bit error and the burst error. This is many more types of errors occurs in the optical communication, but these are the most general and the most common type of error. The error control mechanism may involve two possible ways. First one is error detection and error correction. So, we have come across the different types of errors. So, first of all we have to know how to detect this error, how a device can detect this error, and then come, if we have detected the error, then we go through the correction process of the error. So, the most commonly used technique for the error detection process of the received frames are by parity check and cycle redundancy check, which is also called as the CRC check. So, during the parity check, one extra bit during the parity check, what is going on? One extra bit is sent along with the original bit to make number of ones even in case of even parity and odd in case of a odd parity. So, one extra bit is sent along with the original bit to make one even in case of a even parity and odd in case of a odd parity. We will also go through some examples, so better understanding. So, sender while creating the frame count the number of ones in it. So, there comes an example. If even parity is used and number of ones is even, then one bit with value 0 is added. This way number of ones remains even. If the number of ones is odd, to make it even, a bit with value 1 is added. So, what is this? Is at the sender end. Your sender used to send one extra bit along with the original one. So, if we are having the even parity, so let us see which extra bit can be added. 1 0 0 1 0 0 1. So, how many bits are here? 3 7 bits are here. But when the even parity is used, 1 0 0 1 0 0 1 1 1. One extra bit 1 is added for making the even. So, the receiver, at the receiver section, what is going on? The receiver simply counts the number of ones in the frame. At the receiver section, what is going on? Receiver simply counts the number of ones in the frame. If the count of ones is even, the even parity is used and the frame is considered to be non-corrupted and it is accepted. So, at the receiver section, again the receiver counts the number of ones, and if the number of ones is even, that means even parity is used and frame is considered and to be non-corrupted and it is accepted. If the count of ones is odd and the odd parity is used, then the frame is still not corrupted. So, when we can easily say that for even parity, if the count of 1 is even, then it is accepted and it is said to be non-corrupted, and for odd parity, if the count of 1 is odd at the receiver section, then it is said to be not corrupted. So, we can easily have it here. We can count the number of ones plays a very important role. Now, what is going on in the cycle redundancy check, which is a CRC. CRC is basically a totally different approach to detect if the receiver frame contains valid data, and this involves the binary division of data bit being sent. In this case, the sender and the receiver both performs the binary division process. In for the sender performs the division operation, and what he used to say? He used to say bit being sent and the remainder which comes after the division process is also sent along with the original data. Before sending the actual data, the sender adds the remainder at the end of the actual bits. An actual bit plus the remainder is called the code word. So, what is going on here? We will see with it one example. You can have here, this is the data at the sender end and at the receiver end. So, for example, we have to send a data 11001. Okay. And what is going on at the sender end? At the sender end, we are going to see this is the bit 11001 which we want to be sent, and here the divisor, at here the divisor 101. At the receiver end also we have to maintain the divisor same, we can't able to change the divisor. What divisor we have used in the sender end is itself used in the receiver end also, we can't change the divisor. So, now see, when we divide, we go through the binary division of this number with 101 as the divisor, what we are getting? We are getting 10 as the remainder. So, what the sender will send? Sender will send 11001 and the remainder also. This 10 is the remainder. This is also sent by the sender, and this is called the code word. So, what we are seeing? Original bit plus remainder are sent. Original bit plus remainder after the binary division are sent, and this is called the code word from the sender end. So, or now the signal is sent from the sender end and now it is received at the receiver end. So, what is going on the receiver end? You are saying divisor remains the same. So, that is why using the same CRC divisor, it is already mentioned in the statement also. So, same CRC divisor we have taken, and what the data? Original bit plus remainder. So, original bit is 11001, 11001 and 10 which is our remainder. Again we have to go through the binary division process, and if the remainder which comes is equal to 00, then we can say that the signal is uncorrupted and we will accept, the receiver will accept the signal. If the remainder contains all 0, the data bit are accepted, otherwise it is considered as some other corruption occurred in the transmit. So, this is our cycle redundancy check, which is also called as the CRC check. Now, we have come across the errors, we have come across the different methods of the error detection. Now, if the error occurred, we have to correct it. So, this is some of the two of the common most general method of error correction. The first one is the backward error correction, the second one is the forward error correction. So, what is meant by the backward error correction? When the receiver detects an error in the received signal. Now, can I ask, anyone will answer? If someone asks you, you can easily say by which method an error can be detected, by either CRC check or by the what? We have gone through parity check. CRC check and the parity check are used for the error detection process. So, when the receiver detects the error, it requests back the sender to retransmit the data unit. It requests the sender to resend the data. It is simple work and can be efficiently used where retransmitting is not very expensive, that it is called as the backward error correction, because we in this case we request back to the sender. This is the sender, this is the receiver, and if error detected at the receiver section, receiver send the information to the our sender to retransmit the data. Backward process goes on, that is why it is called as the backward error correction. Next comes the forward error correction. When the receiver detects some error in the data received, it executes some error correcting code which helps in auto recover and to correct some kind of error, then it is called as the forward error correction. In the forward error correction, receiver does not send the data, ask the sender to resend the data. Receiver itself goes through some error coding correction technique to correct the errors. then it is called as the forward error correction. Now comes the eye diagram. Eye diagram is a very important one, the important parameter at the receiver section for detecting the receiver performance. So, it is called as a eye because at last we can able to see that something eye like structure comes into existence in this technique and which decide the different parameters of a signal. That is why it is called as the eye diagram. The eye diagram is a powerful measurement tool for assessing the data handling ability of a digital transmission system. Measurement or assessing the data handling capability. It is used extensively for evaluating the performance of a wireless system and also applies to optical fiber data links. The eye pattern measurements are made in the time domain. We have to already we have a knowledge that we have generally have a time domain, space domain, frequency domain. We talk about the various types of domain in which we do analysis. In this particular we do in the analysis in the time domain and allows the effects of wave distortion to be shown immediately on the display screen of the standard BER test equipment. So, now the different structures of the eye diagram decides the various parameters of the our performance of a signal. So, height of a eye opening. Height of a eye opening at the specified sampling time shows the noise margin. You have to remember this point that the height of a eye opening basically shows the noise margin or immunity to the noise. Let us look at the eye diagram here. So, this height we are talking about, this height we are talking about decide the noise margin or immunity to the noise. Width of the eyes opening, you can have seen the eye diagram. So, now the width of the eye opening, it defines the time interval over which the received signal can be sampled without error due to interference from the adjacent pulse. So, what defines the width of the eye, what defines what? It basically defines the time interval over which the received signal can be sampled without error due to interference from the adjacent pulse, which we called as the inter-symbol interference. I think all of you have remembered the ISI word, inter-symbol interference. Is our ISI. The best time to sample the, so by seeing the eye diagram, we are able to decide the best time at which the signal can be sampled so that the signal can be of error free. The best time to sample the received waveform is what? Is when the height of the eye opening is largest. So, again look at this, we can have the decide this eye diagram, we can able to see height, we can able to see width. So, when the width is the largest one, then in that case we can say that the our signal is error free at that particular time, and this is the best time for sampling the received waveform. Again, when height decides the noise margin and width decides the error, and both has to be in the maximum so as to achieve the good results. The more the eye closes, the more difficult it is to distinguish between 1 and 0 in the signal. So, when the eye closes more, then we can, it is very difficult to distinguish between 0, 1 and 1 in the signal. We are talking about a digital signal, that is why here it will always used to have a 0 and 1. So, when the eye, if someone asks, this is one of the eye diagram 1, and this is the another eye diagram too. In both the case, we are able to see that in which case width in this particular case is larger because eyes are opened very wide, and in this something less, that in this case the to distinguish between 1 and 0 is somewhat difficult than the second one. In second one it will be easier than the first one, we can able to compare. Now, in the thing which is comes the noise margin, height of the eye opening, height of the eye diagram decides basically our noise margin. So, what is the noise margin? It is the percentage ratio of peak signal voltage V1 for an alternating beat sequence to the maximum signal voltage B2 as measured from the threshold level. So, from the threshold level, percentage of the ratio of the peak signal voltage V1 to the maximum signal voltage V2. This gives the noise margin. Now, the time errors, the rate at which all these parameters can be decided with the eye diagram, that is why we are discussing that here in under the heading of a eye diagram. Timing error, the rate at which eye closes as the sampling time is varied, that is the slope of the eye pattern slides, determine the sensitivity of the system to timing error. So, rate at which eye closes as the sampling time is varied. So, rate at which the eye, sometime eye get broadened and sometime eye get closes, sometime eye is open and again it closes. So, the rate at which this eye closing process occurs as the sampling times is varied decides the sensitivity of the system to timing error. The possibility of timing error increases as the slope becomes more horizontal. So, when the probability of timing error increases as the slope become more horizontal. Now, there comes the timing jitter. It is referred to as the edge jitter or the phase distortion. It arises from the noise in the receiver and pulse distortion in the optical fiber. So, what are the responsible, which things are responsible for this edge jitter or the timing jitter, or we can say the phase distortion? Noise in the receiver and the pulse distortion which occurs in the case of a optical fiber. Causes are bit errors, produce uncertainty in clock timing, receiver can lose synchronization with the incoming bit stream, therefore incorrectly interpreting logic 1 and 0 pulses. So, these are the causes which occurs when the timing jitter occur. It causes a bit error, produce uncertainty in the clock timing, receiver can lose synchronization with incoming bit stream, that whether 1 is received or whether the 0 has been received, and it is calculated by the amount of distortion TB at the threshold level to the our bit period TB. Rise time, which is already known to us, that is defined as the time interval between the points where the rising edge of the signal reaches 10% to its final amplitude, where it reaches 90% of this final amplitude is called as the rise time. But for the conversion, 20 to 80% are normally taken as compared to the 10 to 20%, and here is a conversion of this. Because in general practical condition, 20 to 80% basically defines the rise time, 10 to 90 is the ideal condition. Now just look at this diagram. This is the eye opening. We can say dark, P dark current, off condition where we have a 0, then here B1 on, B of 0. Dark current when no signal is, B dark means when no photon is incident on the photodiode. So, these are an eye jitter basically at this region, at the margin basically eye jitter occur, 0 crossing area and overshoot on the logic 0, rise time is taken 20 to 80%, 80% here and the 20% here, eye opening, height and the this is the width, and each parameters basically decide the different values of the receiver performance or the signal performance. We can say this is a little bit complicated diagram. The simplified version of the eye diagram can be like this. So, this is the best sampling time. We have seen in the theory part that best sampling time is when the eyes is fully opened. So, it is the best sampling time, because at this condition we can have a full opening of the eyes. Threshold value, maximum voltage V2, noise margin, and this is the width and this is the height. Height describe the noise margin and the width describe the error. So, here is the, you have to remember this diagram, because this is a very commonly asked question in the case of our optical communication receiver part. And so, just for the concluding part, we are just have a look at the different things which we have studied in this particular lecture. In this particular lecture, what we have gone? We have gone through the various errors which are occurring in the system at the receiver end of the optical communication. Then we have gone through the different methods of detecting the errors. Then we have gone through the, of course, different correction process of the errors. When at last we have discussed about the eye diagram, and eye diagram is one of the most important parameters of the deciding the receiver of working. And what are the different parameters which can be decided with respect to eye diagram? First one is the height of the eye. What indicates? Height of the eye indicates the noise margin or the immunity to the noise. Width of the eye opening decides the time interval over which the received signal can be sampled without error. And then we have gone through the timing errors, timing jitter, which can be shown in our eye diagram for deciding the various parameters. Then we have gone through the rise time, which is between the 20 to 80% in the case of a optical communication calculation. And this is the eye diagram, and this is the simplified version of the eye diagram. So, thank you for attending today's class.